Good morning, students. Chapter 11, Thermal Properties of Matter. In last lecture, we have discussed some quantities related to radiation. Okay, every object, according to its temperature, it emits electromagnetic waves. Now see, if you are given any object, then thermal radiations emitted by body, it consists of waves, electromagnetic waves of different wavelengths, or you can also write frequencies, and these wavelengths of waves form a continuous loop. Continuous loop means all wavelengths, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, dash, 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 dash. Okay, so thermal radiation emitted from a body consists of waves, electromagnetic waves of different wavelengths, and such wavelengths of waves form a continuous spectrum. Okay, each and every value, lambda 1, lambda 2, lambda 3, lambda 4, dash, 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 each and every. But at given temperature, number of waves for some particular wavelength, are more. Okay, yes, this point you have to remember. Okay, but at given temperature, number of waves for some particular wavelength are more. It means, for example, it is one object, radiations emitted. Okay, suppose temperature of this body is T1. So yes, it emits radiation having waves of different wavelengths, means continuous wavelength, lambda 1, lambda 2, lambda 3, lambda 4. But at particular temperature, numbers of waves of some particular frequency are more. So for example this. So what happens at temperature T1, it emits radiation of all wavelength, but these waves are more in numbers, means intensity of this radiation is more. Another radiation having lower intensity. If temperature is changed, suppose now temperature of this object is T2, changed. Okay, then yes, then yes, another wavelength. Okay, now if temperature is changed, then according to this temperature, numbers of waves of some particular frequencies emitted are more. So for example, it is lambda. Okay, it emits radiation of continuous spectrum having all wavelengths, but at some particular temperature, some waves are produced like this. Okay, their numbers are more, their intensity is okay. So yes, this point you have to remember. Okay, at some particular temperature, waves of some particular wavelength, they are emitted more. Simple. Okay. it is given one example. Okay, if it is black body at room temperature, means at 300 Kelvin. So yes, radiations emitted of different wavelength, but which waves are more? Having wavelength 9550 angstrom. These waves are more. Simple. Okay. If I change this temperature, then numbers of waves having some different wavelength will be more. Clear? Okay. As temperature of body increases, numbers of waves having smaller wavelength increases. Okay, so this one relation you have to remember. Clear? Okay. Now there is one graph actually for total emissive power versus the intensity. For total emissive power versus wavelength. It is total emissive power versus wavelength for particular temperature, and that graph is given like this. Okay, and yes, from this graph it is concluded that okay, it is total emissive power, it is wavelength. Okay, so this graph was actually given by Wien. Okay, and from this graph we also give one equation that is called Wien's displacement law, and it is written as okay, lambda, that is wavelength. See here, from this temperature of body increases, numbers of waves of smaller wavelength increases. Means as temperature increases, wavelength of radiation, electromagnetic wave emitted becomes smaller. So there is inverse relation between them. So yes, we can write it, lambda is inversely proportional to 1 upon T. And from this we can write that lambda into T is equal to, it is constant. Lambda into T is equal to, it is constant. And it is called Wien's displacement law. Okay, lambda into T is equal to constant. You can also say this one, okay, lambda is proportional to 1 upon T. And this constant, it is called, this constant is equal to, it is 2.9 into, it is 10 raised to minus 3. What is its value? Lambda its unit is meter, and temperature its unit is, it is Kelvin. So yes, this one point you have to remember. Okay, lambda T is equal to, it is constant. Lambda T is equal to constant. Yes, you can solve numbers of questions from this equation. Okay, so yes, it is Wien's displacement law that you have to remember. Okay, yes. Now next one is another law that is called Stefan Boltzmann law. What is Stefan Boltzmann law? Okay, first of all I will write its equation so you can easily make its statement, that is W is proportional to T is to 4. Now what do you mean by W? W in previous lecture we have discussed. W is called total emissive power. So what is Stefan Boltzmann law? A total emissive power of body is directly proportional to fourth power of its absolute temperature. So yes, this one you have to remember. Okay, what is Stefan Boltzmann law? The total emissive power of body is directly proportional to fourth power of its absolute temperature. That is, W is proportional to T raised to 4. Now, if we remove proportionality, we have to add some constant. So V is equal to, it is sigma E T raised to 4. Okay, where you know W is called total emissive power, T is absolute temperature, E means what? So E is called emissivity. E is called emissivity. And what is sigma? Here sigma is called Stefan Boltzmann constant. It is called Stefan Boltzmann constant, and its value is, the sigma is equal to, it is 5.67 into 10 raised to minus 8. Stefan Boltzmann constant, sigma is equal to, it is 5.67 into 10 raised to minus 8. How to write its unit of sigma? So if you make sigma as subject here, so sigma is equal to, it is W upon E T raised to 4. W, that is total emissive power. Its unit actually we have discussed in last lecture. Okay, that total emissive power, its unit is watt meter raised to minus 2. And watt meter raised to minus 2. T, that is emissivity. It is dimensionless. T raised to 4 means I can write it is K raised to minus 4. It is K raised to minus 4. So it is value of Stefan Boltzmann constant. It is unit of Stefan Boltzmann constant. Okay. From this equation, it is equation of actually total emissive power. Now we know what is equation of W. That is T upon AT. So I can write this as sigma E T raised to 4. Or E, that is energy radiated. That is energy radiated. Energy radiated, its equation E is equal to, you have to write this in this side. So it is sigma E A T raised to 4 into T. Yes, this equation you can use. See, there are two different equations. Okay, this equation W is total emissive power and E means energy radiated. That is E. Sigma E A T raised to 4 into T. Okay, so yes, it is Stefan Boltzmann law, and this equation is again important. Yes, this equation is again important. Clear about this? Okay. Next one. Okay, if you are given it is body, its temperature is T, and it is surrounding, its temperature is Ts. Then we know that body which absorbs, body emits some energy as well as it also absorbs some energy. Okay, so what is net rate of heat loss? Net rate of heat loss. How to find that? Okay, so see here we will see. Okay, if temperature of body is T and temperature of surrounding is Ts, then net rate of heat loss, heat emitted, it is dQ upon dt. dQ upon dt is equal to, it is sigma EA T raised to 4 minus Ts raised to 4. dQ upon dt is equal to sigma EA T raised to 4 minus Ts raised to 4. This equation you have to remember. Okay, so it is Stefan Boltzmann law. So yes, in this lecture we have discussed two laws, that is means displacement law, and second one is Stefan Boltzmann law. You have to remember these equations. Lambda t is equal to constant, and that constant is equal to 2.9 into 10 raised to minus 3. This Stefan Boltzmann law, this equation, the second one, and this third one. Okay, and also remember value of the Stefan Boltzmann constant, that is 5.67 into 10 raised to minus 8 volt meter raised to minus 2 Kelvin raised to minus 4. Okay, so yes, two theories. This is it. Okay, next topic is Newton's law of cooling. Cooling, what do you mean by cooling? See, for example, if in a vessel you have hot tea, okay, yes. If it is placed in surrounding having temperature Ts and temperature of this hot tea is T, and yes, T is greater than Ts. Obviously, it is hot than surrounding, means this room temperature. Then what happens? Yes, after some time, this hot tea will be at room temperature. After some time, it will be at room temperature. Means there is loss of heat. There is loss of heat from this system to surrounding. That system to surrounding. And yes, it is called cooling. It is called cooling. Cooling means heat is lost by object and its temperature, so yes, its temperature decreases. Yes, we know these 2 points. Okay, what is meaning of cooling? Cooling means heat is lost by any object. If object loses energy, if object loses heat, then it is cooled. Okay, so yes, its temperature decreases, heat is lost. Clear? Okay, what is Newton's law of cooling? Okay, Newton's law of cooling gives idea about rate at which temperature decreases or heat is lost. Okay, that is actually depend on difference between system and surrounding. Okay, if temperature T and here it is Ts. Okay, if temperature of this T is 90 degrees Celsius, okay, and temperature of surrounding is suppose 30 degrees Celsius, means this temperature difference is more. Temperature difference is more than, according to Newton's law of cooling, the rate of decrease of temperature or rate of loss of heat energy is directly proportional to this temperature difference. Means if temperature difference is more, it will cool in smaller time. Simple. Okay, what is actually its statement? Statement is rate of loss of heat energy or rate of decrease in temperature of body is directly proportional to temperature difference between body and surrounding. Yes, this one you have to remember. Okay, rate of loss of heat energy or rate of decrease in temperature of body is directly proportional to temperature difference between body and surrounding. This one you have to remember. Now, if you are given object or body having mass m, you want to change its temperature by delta T. Then what is amount of heat required? Amount of heat required to change temperature of m kg body by delta T. What is equation? Yes, delta Q is equal to it is mc delta T. Delta Q is equal to it is mc delta T. Now, if I am taking rate of heat transfer or rate of temperature, then rate of this heat transfer, or I can say rate of heat loss, that is dq upon dt is equal to it is mc dt upon dt, but here I will write minus. dq, why dq dt है? Due to small change in time. So delta q is equal to mc delta t. From this equation I can write dq upon dt is equal to minus mc dt upon dt. Why minus sign? Minus sign is due to temperature decreases. Yes, due to loss of heat, temperature decreases. That's why here we have to write minus sign. Clear about this? Okay, so now according to Newton's this law of cooling, I can write dq upon dt is equal to minus mc dt upon dt is directly proportional to T minus Ts. What is T minus Ts? T is temperature of body and Ts is temperature of surrounding. Yes, T is temperature of body and Ts is temperature of surrounding. So from this I can write Cm, mass of body. If I am saying that mass of body I am taking constant, C, that is also constant. So I can write from this dt upon dt is proportional to minus T minus Ts. I can write this minus this side. So from this dt upon dt is equal to, if we remove proportionality, we have to add some constant, and that constant is k dash, T minus Ts, where k dash is constant. So this dt upon dt, it is called rate of decrease in temperature. Okay, K constant. What is T? T is temperature of body. What is Ts? It is temperature of surrounding. Clear? So yes, this equation for Newton's law of cooling that you have to remember to solve questions. Okay, dt, this dt means it is change in temperature. This dt means it is time. K constant, T temperature of body, Ts that is temperature of surrounding. So yes, it is Newton's law of cooling that you have to remember. Okay, what is Newton's law of cooling? Okay, again I say rate of decrease in temperature, that is rate of cooling. Rate of decrease in temperature, or you can say it is rate of cooling. Yes, it is rate of cooling. It depends on this temperature difference. So temperature difference is more, it will cool earlier. Okay, and if temperature difference is small, it will take some time. Yes, it will take some time. Clear? Okay. So yes, it is Newton's law of cooling. Okay, and I think this is it from this chapter. All theory is completed. Now we will see questions from this chapter.